Welcome to Maths Laundry. Today, we are visualizing how to count different types of relations on a finite set with n elements. We count these relations using an n by n grid. First, let's look at the total number of possible relations. In a binary relation, every pair of elements a, comma b is either related or it isn't. Visually, this means every single cell in our grid has two possibilities. It can be empty or filled. Since there are n squared total cells and each has two choices, the total number of distinct relations is 2 raised to the power of n squared. Next, let's count reflexive relations. By definition, a relation is reflexive if every element is related to itself. On our grid, this imposes a strict constraint. The main diagonal must be filled. These n cells are fixed to 1. They are no longer a choice. However, all the cells off the diagonal are still free to be chosen. Since we removed n cells from our set of choices, the exponent reduces. The formula becomes 2 raised to the power of n squared minus n. Now, let's consider symmetric relations. This means if A is related to B, then B must be related to A. The diagonal elements are their own mirror images, so they are independent. We can choose them freely. But for the rest, the choice is coupled. Once we determine the upper triangle, the lower triangle is forced to match it exactly. We only get to choose the cells in the upper triangle and the diagonal. Summing those up gives us the formula 2 raised to n times n plus 1 divided by 2. Fourth, we have transitive relations. This states that if A relates to B and B relates to C, then A must relate to C. Unlike the previous examples, this doesn't create a simple geometric pattern on the grid. The constraints interfere with each other in complex ways. In fact, there is currently no known simple closed form formula to count transitive relations for a general n. Finally, equivalence relations. These are relations that are reflexive, symmetric, and transitive. Counting these is the same as counting the number of ways to partition a set. These counts correspond to the Bell numbers, denoted as Bn, which is a recursive recurrence relation involving binomial coefficients. To use the recursive formula, we first need our base cases, B1 and the special case B0. First, B1. If our set has just one element, there is only one way to partition it, the set itself. So, B1 equals 1. Now, B0. How many ways can you partition an empty set? In combinatorics, we define this as exactly one way, the empty partition. It's the same logic as why 0 factorial equals 1. So, B0 is also 1. With our base cases, B0 equals 1 and B1 equals 1, we can climb the ladder. To find B2, we'd use B0 and B1. To find B3, we'd use everything up to B2. Let's skip ahead and calculate the fifth Bell number, B5. To find B5, we sum from k equals 0 to 4. We take 4 choose k multiplied by the previous Bell number bk. Substituting the values, we get 1 times 1 plus 4 times 1 plus 6 times 2 plus 4 times 5 and finally 1 times 15. Simplifying this arithmetic gives us 1 plus 4 plus 12 plus 20 plus 15. Summing these up gives us 52. There are exactly 52 equivalence relations on a set of 5 elements.